So today we are going to learn about universal gates, but in a detailed format. Why they are called universal gates? Because in the previous videos, if you look carefully, if you have gone through the previous videos, there we have stated that yes, universal gate is another kind of logic gate, but it was not explained properly due to time constraint. The video was getting larger. That's why today, now in this video, I'm going to show you why universal gates can be, how, why they are called universal. Okay, so the first universal gate was Nand gate. Okay, so these Nand gates, and another universal gate was NOR gate. So these NAND and NOR gates can be converted back to the original, basic gates. How? We know basic gate, the first basic gate is a NOT gate, which looks like an inverter, okay? NOT gate. So how can you convert a NAND gate into a basic NOT gate? You might have a question in your mind now, okay? Because if we look carefully, NAND gates have the symbol like this, basically, okay? So if you want to convert a NAND gate into a NOT gate, how is this possible? Because it has two inputs. So if you short these two inputs, now you can see it can be easily converted to a NOT inverter gate, isn't it? So I hope you are getting my point. This is the situation for NAND. Okay, so you can try similarly OR gate. Okay, let's try the AND gate first. Okay, AND gate is basic multiplication. This is AND. Next we will try our OR gate. Okay, so if you want to represent AND gate but using only NAND gates, how is this possible? We know this AND is actually invert of NAND, or you may say NAND is invert of AND, vice versa, isn't it? So now if we try, let's draw one NAND gate first. Okay, so you have, let's say, A and B as your inputs. So your output here will be AB bar. But you want your AND operation, which means you want AB in your output. Okay, so how you can do it? If you use one inverter form of NAND gate. If you use one inverter form of NAND gate, surely you will get your desired output. Okay, so this is possible. So similarly, let's try for OR. But for OR, there is one problem. You need to make sure that you have A plus B. But we know NAND is, in multiplied format. How this can be made into A plus B? If we try using some De Morgan's or something like that, maybe it is possible. So let's try it using designing first, okay? Because we are trying to learn the designs first. So let's say this is your A input, and you will have another input which is B. So if you pass these two inputs through inverters, you are getting A bar. Okay, similarly you are getting B bar here. So now next, what will be the case? Next, if you add one NAND gate here, okay, your output is supposed to be A bar dot B bar whole bar. If you apply De Morgan's according to this complement rule, okay, so what does it become? Let's see. A double bar plus B double bar. So obviously it does look like A plus B, isn't it? A plus B. So what was our target? To make our what gate? This is our OR gate, isn't it? So we will try this basic gate operation using Nand in the multisim now. Okay. So now what we are supposed to do, let's place our components. Okay, let's place our components. So we can find from the previous video, if you go to sources, select digital source. Okay, just continue. Just place one source. We are trying to make our first gate, which was NOT gate, using inverters, using inverter form of our NAND. Okay, so since NAND is already selected, we can just place it. Okay, after placement we are going to add our, let's say, any indicator. Okay, we can select probe, select any color, and just connect. Okay, so we need to short it first actually. Okay, let's short it and then connect using wire. Okay, and now if you try to run the simulation, you will see exactly for 0 inverted output, for 1 inverted output. Okay, 1, the output is 0, low, isn't it? So now we can try the next combinations, which is AND gate representation. Okay, AND gate representation of our AND gate representation, but using NAND. So we need 2 inputs. So next we need our IC. Okay, NAND IC. So NAND, we can place it, let's say any series. Okay, NAND, one NAND for usual NAND and another for our inverter form. Okay, after that we need our indicator. Okay, any color, let's say green or orange. Okay, orange color. So now our next target would be to connect it. So we have made the second designing. Okay, this is for AND. So this part right here is basic NAND gate that has been added with a inverter form of our NAND gate, and then just I have just connected these. So now hopefully if we try our simulation AND gate, if you remember the truth table, let's try to remember the truth table of our AND gate. 0 0, for multiplication situation it is supposed to be 0. If we take 0 1 also, the output is supposed to be low as well. If we take 1 1, then only the output was supposed to be high for AND gate. Remember, it is working, behaving like an AND gate now. If we take even 1 0, another combination, so it also shows 0. Okay, so now next, okay, these two gates, which is our OR gate, AND gate, is complete. Now we will try the our NOT and AND. Okay, NOT gate, AND gate is complete. Now we are going to try the OR gate representation, which is this format. So let's fast do it. Okay, so I'm going to stop the simulation and place our components. Okay, what components do we have? We have the sources, 2 sources we need to place, source number 1 and source number 2. 2 variables, let's say A and B. After the variables are taken, we are supposed to collect our NAND gate. How many NAND gates do we need? If we go back to the design, we can easily see one for A bar. Okay, another is for B bar, another is for making the A bar dot B bar whole bar, and done. Next is we need our last component, which is showcasing the output. So you can select any colored light and just place it. So now our next task would be to connect. Okay, so we can just short it anyhow you want. Just take a wire and connect. That's it. Next, just connect with the NAND, next NAND gate. Okay, it is not connecting. 1 minute. Okay, connection is done. Next is connected with the probe, and now we can run the simulation to check for our OR operation. So whenever you are doing two numbers of addition, okay, two variables, if the two variables both are low, so what will happen? 0 plus 0, the result, desired result will be 0. If you are adding up 0 plus 1, it is supposed to be high, so OR gate. So it will be satisfied eventually. If you add 1 plus 1, you are getting 0. Sorry, 0, no, you are getting high. Okay, 1 plus 1 equals to high. If you take 1 plus 0, you are getting high as well. So this is the possible 3 basic gates using universal gate, which is NAND gate. So you can try, okay, instead of basic gate also, if you want, you can also try to make Xor. Okay, another gate was Xor gate using NAND. If you want, you can also make NOR. Okay, this is our NOR gate using NAND. It is also possible. And the last one would be XNOR. Okay, let me draw it here. So these were the gates that we have seen from the video of logic gates. Okay, so what are we supposed to do? Let's make the XOR first. So XOR, if you remember the expression A B bar, okay, let's write it. A B bar plus A bar B. Okay, this was our expression. If you want to write the expression for this gate right here, NOR gate, it will be A plus B whole bar. So if you want to make using NAND, this is possible. If you want to make using NAND XNOR as well, this is also possible. So XNOR was, what was our expression? Let's recall. Okay, AB plus A bar B bar. So now let's try to draw it. Okay, let's try to draw our NAND gate representation for XOR. So how we can do it? Let's take A, B first using NAND. Okay, next we will try to understand the steps. Okay, and then we can design it in the multisim. Okay, so you can take another one here. So here you have, let's say, A, and here you have B input. Okay, so A and B. So how is this working? In order to understand this, let me zoom in a bit and let me show you how this is working. Okay, so here you will have, okay, let me change the color. 1 minute. here you will have A, B bar. This is the place where you're going to get AB bar as your output. This is the place where you will get A into AB. Just remember one thing, this is a NAND gate. So always whenever multiplication has to be done, make sure you have your respective complement. Similarly, you can try with the next one, okay? This is possible. So next, what will happen? You need to simplify it, okay? Let's simplify it. So you can apply De Morgan's here. So what will happen? A bar, okay, plus AB whole bar, isn't it? If you apply De Morgan's here, AB whole bar, which means AB whole bar, which means actually it is becoming AB. Similarly, if you simplify this one as well, you are going to get B bar plus AB whole bar, which means A, B, isn't it? So here you are going to get the output. Let's say Y is your output. Y will be A bar plus A, B, okay, A bar plus AB multiplied with, okay, A bar plus AB multiplied with B bar plus A, B. So this is multiplication, and after that there will be one complement, isn't it? So now you can simplify here in the next line. If you apply De Morgan's, what will happen? A bar plus A, B, okay, this is supposed to be whole bar plus A bar, sorry, not A bar, actually it will be B bar, okay, one mistake, okay, it will be B bar plus AB and whole bar, isn't it? So next, let's write the next line. So if you apply De Morgan's here, you will have A into AB whole bar plus, okay, plus you will have B double bar, okay, only because of B double bar, B into AB whole bar. So now what can you write? You can write De Morgan here again. So A into A bar plus B bar. I hope you are understanding. Okay, next is B A bar, just applying the De Morgan's everywhere. Okay, there are two kinds of De Morgan's theorem. One is when you have multiplication. Okay, one is when you have multiplication and a complement, then it is supposed to be summation and complement above each variable. Okay, that we have done. Another is when you have summation between two variables, then after applying De Morgan's, what will happen? Multiplication and complement above each element, okay, each variable. So now if you do A dot A bar, I hope all of you remember the rules of Boolean algebra. A dot A bar becomes 0, okay, plus next you will have A B bar, isn't it? Just taking the bracket off, plus you have A bar, B, you can get easily, and next B dot B bar will become 0. So now in the next line, if you cross out the zeros, you are getting A B bar plus A bar B, which is equivalent to your given main equation that you have decided previously, isn't it? So now if I zoom out, this was our circuit, so we can try to implement this XOR gate in our multisim. Okay, let's try to do it. So what are we supposed to do? We are supposed to stop the simulation. Okay, let me make this circuit here, okay, so that you can see the circuit and also implement as well. Okay, this is our circuit. So now we are going to place the components. Let's place it. First is the sources. Okay, so let's bring the sources. First we have two sources, one is source A, another is source B. Next we need to bring our gates. Okay, how many gates do we have? NAND gates. Okay, 4, 1 2 3 4 4 NAND gates. We don't have to short anything, just connect it accordingly. Okay, so we can place 4 NAND gates. So let's go back to all groups section. NAND gate is already selected, just place the 4s. Okay, so let's take number 1, number 2, number 3, and the last one here. After that you need one indicator, that's it. Okay, indicator. So take a probe and then connect. Okay, after that you're just supposed to use the connections, that's it. Okay, so how have I connected? Just according to the diagram that I have drawn before previously. So you can just connect it. After connection, make sure to run the simulation. Okay, just run the simulation. Okay, so now we are going to check for XOR operation. If we remember the truth table of XOR from the previous logic gates video, okay, if you just go through, for XOR, for any unequal combination, whether it's 1 0 or 0 1 combination of inputs, the output is supposed to be high. So let's take 0 1 combination as well. You can already see that it is high, but for 1 1 combination it is low. So this was all about XOR gate operation. So now we can try to make a gate for NAND. Okay, using NAND, just you are going to design NOR gate. Using NAND, you are going to design NOR gate. So how can we do it? We can take, if we apply De Morgan's here, okay, it is supposed to be A bar, B bar. Okay, so if we make A bar and B bar first, which means we can easily make NOR gate if we have our OR here. Okay, just we need to redesign this OR first. After designing the OR, we can just add one inverted representation of NAND, isn't it? If we do like this circuit will be exactly equivalent to NOR gate. I hope you are understanding. So let's try to design it in our, okay, design the circuit where in the multisim. Okay, so we are going to focus for this design. Okay, so we are going to place the components first. So we are focusing for which circuit? This one. Okay, let me highlight it for you. So we are going to place our first input, which is sources. Okay, first source should be here, second source should be here. Okay, we need our all groups from where we can select our NAND gates. So NAND gate number 1, let's say for this A inverter, NAND gate number 2 for B inverter, NAND gate number 3 for the this one, okay, third gate, and then the last is last inverter. Okay, after that we need to add our indicator. Okay, let's take any color and just place it, and now we are ready to make the connections. Okay, so firstly we need to invert it first. Okay, now just connect, and then just invert again, and we can start simulation. So it is supposed to work like a NOR. So for NOR gate, if we remember the truth table, OR was for 0 0 it was 0, for 0 1 it was 1. I mean the combination for output of OR was 0 1 1 1. So for NOR, which is invert of OR, it is supposed to be high. For 0 0 combination, as we can see, the output is high. If we take 0 1 combination, output is low. If we take 1 1 combination, output is low. If we take 1 0 combination, also output is low. By the way, if you hear any water flow, any sound for water is flowing or something like that, you must understand that it is raining. Actually, you can hear thunders also. If you can hear some sound in the background, the sound is coming because it is raining here, and I am doing the video from Dhaka, so from my home. Anyways, weather was unpredictable. I could not understand. It was really sunny before I started the video, and now it's totally gloomy and rainy season, rainy day. So now, since our NOR gate is obviously complete, now we can proceed with our next gate, which is XNOR. Okay, the last one, XNOR. So how you can design XNOR? Let's design. You can see already XOR done here. Okay, so if we try this XOR with another kind of inverter, if we add inverter here, won't it be XNOR? I hope you are understanding. If XOR is added with one complement, then what happens? You are actually placing the complement over this particular equation, isn't it? Let me zoom in. I hope it will be clear. So what I was saying is, this was our circuit for XOR. But if we add one inverter here, just after the XOR, then it is supposed to work as a XNOR circuit, isn't it? So let's implement it here. Okay, so we have already implemented our XOR previously. Let me get back. This one was our XOR gate. So if we try, okay, let's delete the wire. Okay, we need to stop the simulation first. Let's delete the wire, shift the wire, shift the indicator a little bit towards your right, and add, just place. We are just modifying the circuit in order to not make the overall video a little bit lengthy. Instead of being lengthy, we are trying to make sure our video is short enough, because you can easily practice your previous circuits. See, really, you're just going to, in order to design XNOR, what you can do, if you have XOR already designed, or if you redesign the XOR, just add one inverter form of NAND gate, and then just what you need to do, play the simulation. You will see on 1 1 XNOR operation, right? Just remember the truth table, just try to recall the truth table of XNOR. For 1 1 it is showing high. For 0 0 0 1, you know, it is low. For 1 0 it will also be low, but for 0 0 combination it is high. So we know already that for XNOR, what happens for XNOR gate, the output is supposed to be high only when you have equal inputs. Okay, either both are zeros, both the inputs are zeros, or both the inputs are ones. So today, since in this video we have already talked about how you can convert the basic, how you can convert the universal gate, one universal gate, which is NAND gate, into the basic gates first we have seen. After that we have implemented exclusive gates, and also we have tried the NOR, another universal gate. We have tried it here. Okay. So I hope all of you will be practicing this in your leisure time, okay, whenever you wish to, for building the knowledge, because in the future videos we are going to try to utilize this basic knowledge that we have from the previous videos, logic gates, exclusive gates, and universal gates. All these knowledge will be utilized to make the combinational circuits in future. Okay, so in the next video, before proceeding towards other complex circuits or combinational circuits or other next topics, we are going to try in the next video to convert from NOR. Utilizing NOR, we are going to design inverter. Utilizing NOR, we are going to design AND, okay, or XOR, XNOR. Similarly, NAND. Using NOR, we are going to design NAND as well. So this was the topic for today. I hope you have understood this video well enough. So in the next video, we are going to talk more about our exclusive gates, our combinational gate, etc., etc. Okay, so many things are there. So please take care, stay safe and healthy, and try to practice these circuits, because eventually it is going to help you for more complex circuits. Okay, so bye for now. See you again in the next video.